I'm Petko from University of Cambridge, and I'll be presenting our work codenamed Leo, or it is a scheduling framework that distributes sensor inference algorithm execution across heterogeneous mobile processors and cloud. And first, I'll begin by saying that I'm sure you all agree energy is by far the biggest limiting factor on battery-powered mobile devices. And in fact, a class of mobile applications that is particularly notorious for draining battery reserves on the mobile device is the class of sensor-based applications, or applications that are continuously monitoring sensor data in the background, data coming from the microphone, the accelerometer, camera, GPS, and there are quite a few examples of such applications. We have, let's say, Shazam. I'm sure that you're all familiar with this application that performs song recognition by continuously sampling the microphone in the background and extracting features, sending them for classification of the song in the cloud. We also have services like Google Now that provide voice-activated services and voice search. And in fact, we have a lot of these applications coming up. They provide a range of services, and users can rely on these services to perform different tasks. We have, however, two problems with these applications. First is they're quite energy hungry, and the second is there is multiple of them. I'm sure you have multiple of them on your mobile device, and they compete for memory and computation on the mobile device. Just to give you an example of the severity of the energy issue on mobile devices and smartphones in particular, let's say you have a 3,200 milliamp hour battery, such as the one of a Nexus 6, and you deploy a speaker identification sensing application that tries to identify the current speaker in a room. And you deploy this application so that it samples the microphone on the CPU and runs continuously in the background with the display off. Well, your battery will be drained in 10 hours. And I assume you agree that this is quite alarming, because you want to use your smartphone for other applications, not just identifying the speaker in the current room. So what we propose is that we can actually consume very little energy with very little overhead, less than 0.5% of the battery daily, and still maintain timeliness guarantees for a range of these sensor-based applications, and still consume up to 3 times less energy than conventional cloud offloading with CPU-bound sensor sampling, and up to 34% less energy compared to a solution that uses cloud offloading in addition to a low-power microcontroller unit, such as a DSP, like the Qualcomm Hexagon DSP, for example. And I'm sure one of the questions you might have is, can we not just one of the existing frameworks that are scheduling at the moment mobile applications, or can we not just a general purpose scheduler to manage the workload of sensor-based applications? Well, the truth is that there are several disadvantages to existing scheduling frameworks, and one is that current scheduling frameworks are too general purpose. Many of them can miss optimization opportunities because they don't know what feature extraction is, they don't know what classification is, and they don't know the data dependencies between the different stages of the processing pipelines that sensor-based applications have. Another problem is that many of these scheduling frameworks concentrate on one of the computational offloading resources, so they'll either use a low-power DSP or they'll use cloud for offloading, but very rarely they use more than one resource to offload computation. And then we have a third problem, which is many of the existing scheduling frameworks are actually quite heavy to be applied to the workload of sensor processing. This is because the continuous sensor stream generates a large number of sensor processing tasks in a short amount of time. And if we frequently schedule with the current frameworks, we actually incur a large energy overhead. And I'll show you examples later to give you an idea of what this overhead might be. So in an attempt to address the deficiencies of existing scheduling frameworks, we introduce Leo, which is a low-power scheduler that tries to jointly optimize the heterogeneous resource use for concurrently running sensor-based applications. It tries to exploit sensor semantics for finer energy control. It maintains a low overhead by running on a low-power unit, and it also reschedules frequently to guarantee the deadlines of sensor-based applications and also be responsive to changes in resource availability and user context. I'll give you an overview. Let's suppose we have a number of sensor-based applications that are running concurrently. In our prototype, we have a series of microphone-based and accelerometer-based applications. We have a workload monitor component that continuously inspects the sensor stream in the background, and it tries to detect relevant events, such as the onset of speech. And in response to such trigger events, or in response to the app logic, it generates sensor processing requests that it places in a sensor job buffer that resides on a low-power unit. And an example of such a sensor processing request is, let's identify the speaker from the last 5 seconds of audio data that you have just collected. We have a low-power scheduling component that runs on a low-power unit. In our case, it's the Hexagon DSP in our prototype. And this scheduling unit continuously monitors the sensor job buffer. It periodically detects the sensor processing requests from that buffer. And in our case, this is a 1 second period. So every second, the scheduler will look at the sensor job buffer for relevant sensor processing requests, and it will try to generate tasks that correspond to the sensor processing pipelines needed to process the data. It also gets feedback from a resource monitor that gives information such as CPU utilization or changing network connectivity. And given this resource information, as well as a set of generated tasks, such as feature extraction and classification, the low-power scheduler, or LEO, generates a schedule that distributes the computations across the different heterogeneous resources. In our case, we support the offloading to cloud, CPU, low-power unit, and a GPU. And LEO makes full use of the heterogeneous resources by adopting a library approach. So we have a library of C routines that are implemented in DSP-compatible version of C. It's compatible with the Qualcomm Hexagon DSP version of C. And we have routines that perform feature extraction and classification that are needed for common type of sensor processing inference, such as mel frequency cepstral coefficients, frequently used in audio analysis, or deep neural network propagation that is also frequently used in speech processing. And in terms of the GPU, we use a library of OpenCL routines. So LEO does a joint optimization of applications and resources by solving a global resource optimization problem. So it formulates a mixed integer linear programming task that takes as input 3 different sources. First is the sensor tasks, as I showed you previously, the sensor tasks that map to the library of C routines that we have developed. Then we have the currently available resources, such as a low-power DSP, the threads of a low-power DSP, or a GPU, or a CPU. And we also need information about the expected runtime and energy of the sensor tasks, or the underlying algorithms that are implemented in our library. So this can be performed offline in a one-time step prior to the deployment of the framework. So LEO exploits sensor algorithm semantics by predefining the partitioning points of the sensor pipelines. And it does this so that it can work on multiple shorter tasks in parallel. I'll give you a concrete example of the speaker identification pipeline. So this pipeline has 2 major stages, feature extraction and classification. The classification is based on Gaussian mixture models. Each speaker is represented by 1 Gaussian mixture model, and the pipeline works like this. It extracts the features and tries to match them subsequently against each of the Gaussian mixture models. The model with highest probability is the predicted speaker. In our case, what LEO does is it knows that the Gaussian mixture models can be evaluated in parallel because there are no data dependencies between them. So you can have, for example, 1 Gaussian mixture model evaluated on a low-power DSP, another Gaussian mixture model evaluated on the GPU, and another Gaussian mixture model evaluated in cloud if needed. So Leo maintains a low overhead by using a heuristic algorithm that is based on a version of genetic algorithms. It's called memetic algorithms. The idea behind these algorithms is that they maintain a population of candidate schedules that are iteratively improved over time with generations. And here I'll give you an example of what a schedule might look like for two example applications, speaker identification and activity recognition. We have two types of computations, feature extraction and classification, and the numbers in each cell show how many computations of that type are assigned to a resource. In this case, let's say for the speaker identification pipeline, we have in total 46 computation types of 46 instances of computational types, which are, in our case, Gaussian mixture models, and 23 of them can be evaluated on a low-power DSP, and 23 can be evaluated in cloud. So Leo maintains a low overhead, first thanks to the heuristic algorithm that generates the heuristic schedule, and then also it runs on a low-power unit, so that it consumes much less power than what it would consume if it were deployed on a CPU, for example. And here, with a 10-up workload of the applications such as the ones that I showed you previously, Leo would need around 100 milliseconds to generate a schedule, and over the course of a day, it will consume less than 0.5% of the battery. In contrast, if we were using the next best alternative for scheduling, which is compute the schedules in cloud so that we don't spend the resources of the CPU on the mobile device, we would consume roughly 7 times more energy, or 3.5% of the battery, and this is just for the scheduling overhead. So I'll give you an example of how Leo compares against alternative solutions, and here we have an example workload of 2 accelerometer-based applications and 3 microphone-based applications. We are scheduling across 4 different resources, and we assume we have cloud connectivity with a 5 megabits per second throughput. So to produce this workload so that we have the sensor-based applications running continuously in the background, we will consume roughly 26% of a 2,300 milliamp hour battery to process the workload of these applications over the course of a day under the schedule computed by Leo. In contrast, if we use a naive cloud offloading solution that uses CPU-bound sensor sampling and performs feature extraction on the CPU and classification, the heavier classification stages in cloud, as is typically done in current applications, we would consume roughly 2.6 times more energy, or roughly 70% of the battery will go just for those 5 sensor-based applications running on the phone. If we use another solution that extracts features on a low power unit and performs classification in cloud, then we have a 24% overhead. If we use a general purpose offloader such as MAUI, we implement a version of MAUI that runs its binary partitioning logic with respect to the low power unit, then we have a 20% overhead. And an interesting thing to observe here is that if we remove the GPU as a resource in our scheduling, we consume roughly the same amount of power as with using the GPU, which means that the GPU is not used in the current schedule, and the reason for that is that the GPU is a power-hungry resource. It is less expensive than the CPU, but given that we have tight deadlines, approaching the GPU frequently for computation is expensive. One scenario where the GPU computation is actually beneficial is when we do the processing offline or we don't have cloud connectivity. In this case, Leo can consume only a fraction of the energy of a version that uses only a CPU and a low power unit. And the benefits are not only attributed to the fact that we are using a low power GPU, but also to some of the scheduling logic of Leo. And to prove that, we implemented a baseline that uses a low power unit and a GPU. And as you can see, it consumes 46% of the energy of a version of Leo that doesn't use the GPU, which is higher than the 38% we could consume if you were using Leo with the GPU. And to summarize, Leo does scheduling of concurrent applications on multiple heterogeneous resources on the mobile device. It exploits sensor semantics for finer energy control. It also runs on a low power unit to save energy, and it performs frequent rescheduling so that it remains responsive to the timeliness requirements of sensor processing pipelines, and it also is responsive to changes in resource availability or changing network connectivity. With that, I'm concluding my talk. I would welcome any questions. Just one more thing I want to mention is that we plan to release a version of the software by the end of this year, so stay tuned for any updates. You can check the webpage if you're interested. Thank you.